Okay, next up in our proving or verifying trig identities is to add to our arsenal a couple of new identities, the sum and difference identities. And those are going to be used when you see an angle, or instead of just one angle, you're going to see two angles, either being added to each other or being subtracted to each other, all within one trig function, okay? Now, what's interesting about this is it becomes an expression that we can end up simplifying it to. And it doesn't even look like we're simplifying it. It looks like we're making it more complicated. But let's talk about what these formulas show us. So we have two angles, okay? And I'm going to highlight those with two colors. Green for U, and I'll use red for V. Now, U and V could be anything. They might be variables, they might be actual values, and in fact, you're probably going to find that it's usually one of each. But what I see is that I end up with U, whoops, I changed colors all of a sudden, U showing up in a couple of different places in each of these formulas, okay? And I also end up with V showing up in a couple of different places in each of these formulas. And depending on which trig function I'm using, you know, like sine, I see sine here and sine here, okay? But with, and I'm going to highlight sine with blue in all of my equations, just to kind of let you see that it's sort of an interesting pattern. And then cosine, we'll do yellow. I forgot a U there. All right, so we end up with sort of this interesting pattern that happens. Now with tangent, we're only using tangent within the equation. But this allows us to do a substitution when we see two angles being added or subtracted from each other. Now, all that being said, let's just prove something that we already know is true. Because cosine of 90 minus theta equals sine of theta, that's one of our identities. That's actually one of our cofunction identities. But I want to show you why that's true. So we're actually using cosine. Whoops. Let me get the highlighter here. We're using cosine, okay? And my angles are 90 and theta. So I'm going to use 90 will be what I put where U is, and theta will be where I put where V is. Now we have to choose the correct identity from our choices. So when I look at my choices, I have two of them that use cosine of two angles added together. I have either this one or I have this one. And the difference between the two is one of them is plus UV and one of them is U minus V. I see that I'm doing a subtraction between the two. So I'm going to want to use this identity. And what I'm going to do is I'm going to rewrite it so that it looks like this. Once again, it looks like I'm making things more complicated, but I promise you it will get better. So let's rewrite it. And I will have cosine of, now let's think of 90 again as our U and theta as our V. So I'm going to have cosine of U, that's 90, times cosine of V, that's theta, and then plus, and I'm just using this formula right here. So I've written this so far, now I'm going to write this, plus sine of U, that's 90, times sine of V, that's theta. And remember, I'm trying to show that that's equal to sine of theta. Okay, so now our knowledge of our unit circle is going to become really important. The first thing I'm going to do is I'm going to ask myself, what is the cosine of 90? What is the sine of 90? Because I have an actual numerical value for an angle, I can do some evaluating. So cosine of 90, think about your unit circle. Up here at 90, you have a value of 0 for x. So I'm going to do 0 times the cosine of theta plus my x value, or my y value is 1 times the sine of theta equals the sine of theta. All right, 0 times cosine is just 0. So I can just write that as 0. And then plus 1 times sine is just sine, and I've got it. So I have 0 plus sine is sine. Sine of theta equals sine of theta. I've proven that that identity is true. Okay, let's go ahead and try another one. So we're going to jump right in and we're going to do the scariest one of all, tangent. So I want to prove that tangent of x plus pi is just tangent of x. So once again, if I just take a second and think about tangent of x. So my x is going to be like my u in my equation, and my pi is going to be like my v in my equation. And I do notice that I'm adding, and that is why I'm going to use the one that I have kind of marked up here. So I'm going to start by rewriting this expression as it's written on the right side of the identity above. So instead of tangent of u plus v, remember we're going to use x is u and pi is v. I'm going to be able to change that to the tangent of x plus the tangent of pi over 1 minus tangent of x times tangent of pi. And again, I'm just trying to show that this is exactly tangent of x. So this is when, again, knowing your unit circle is really important because we have an actual numerical value for an angle here. We do not have a variable anymore, right? Tangent of pi, that's a place on my unit circle. That is a place where I can look at my unit circle and I can evaluate this entire expression because I know the angle. So let's go ahead and rewrite this with the tangent of pi substituted in. So on my unit circle, here's pi, and we know my ordered pair is -1, 0. So tangent is your y value over your x value, so that's going to be just 0. So instead of tangent of pi, I'm going to write plus 0. And then 1 minus tangent of x times, instead of tangent of pi, I'm going to write 0. And I'm trying to show that this is equal to the tangent of x. And now all it's left to do is some simple algebra and some simplification. So in my numerator, tangent of x plus 0 is just tangent of x over 1 minus tangent of x times 0 is just 0. I want to show that that's tangent of x. And guys, look, tangent of x essentially over 1 is what we have because 1 minus 0 is 1. I get tangent of x equals tangent of x, and I've shown that that identity is true. All right, next up, let's not let this look like it's going to be hard for us. It's really not as bad as it looks like. We do have pi over 6 in our equation. Guys, if that really bothers you, change this to 30 degrees if you'd like. Not a big deal. It doesn't really matter which way we write it because we're going to use our formula to change it anyway. So we're going to prove that we've got cosine, and it's a plus, so we're going to use this equation here. And once again, I'm just going to take a second and highlight what's going to correspond to u and what's going to correspond to v here. Okay? So if I rewrite this, I'm going to rewrite it as cosine of u times cosine of v minus sine of u times sine of v. So I'm going to start out with cosine of u times cosine of v. So that's cosine of theta times cosine of pi over 6 minus, and then I've got sine of theta times sine of pi over 6. Now I'm trying to show that it's equal to this expression. Now once again, don't let that scare you. It's not as bad as it looks. Okay, next, I have to know my unit circle because I have an actual value for my angle here. Cosine of pi over 6 and sine of pi over 6. Because I know that my angle is pi over 6 or 30 degrees, I can actually then evaluate that. So think about your unit circle. Pi over 6 or 30 degrees is right here. We've got an x value of radical 3 over 2 and a y value of 1/2. So our cosine is radical 3 over 2 and our sine is 1/2. So I can rewrite this as cosine of theta times the cosine of pi over 6 is radical 3 over 2. So times radical 3 over 2 minus sine of theta times sine of pi over 6. That is just 1/2. So times 1/2. And then I've got the right side of the equation that's still what I'm trying to prove. All right. Now, if you would like to kind of clean this up a little bit, typically you're going to see your coefficient written in front, right? So we would really write this as radical 3 over 2 times the cosine of theta minus 1/2 times the sine of theta. And then I hope that you're starting to sort of put together what's happening here. Compare the two sides. It's always important to look at each side and see what you need to do to make the left side look like the right side. if I look at this, on the right side, I've got a 1/2 factored out in front. Well, let's try that over here and see what happens. So let's factor out a 1/2. If I factor out a 1/2, I'm going to be left with radical 3 cosine of theta minus sine of theta. And then look, that's exactly what I needed. So I was able to prove that those two things are the same. All right, one more. So this is one of my favorites because it looks really complicated. Now I'm going to be really careful about this because I actually have a product happening here. I have this thing times this thing. All right, and that's going to be important to distinguish the differences here. All right, so sine of x plus y, that's just this. Now the only difference is instead of u and v, I'm going to write x and y. Sine of x minus y, that's just this. And once again, the only difference is instead of u and v, I'm going to write x and y. So let's start with sine of x plus y. On the right side of that identity, I'm rewriting it this way now. So instead of u and v, I put x and y. So I'm going to have sine of x times cosine of y plus cosine of x times sine of y. That's the blue. Now the green. So the green says we've got sine of u cosine of v minus cosine of u sine of v, just replacing u and v with x and y. So I'm going to have sine of x times cosine of y minus cosine of x times sine of y. Now, just because I'm going to kind of run out of room here, for a moment, I'm just going to write that as a box, okay? Now comes the fun part. So on the left side, I have a product because I'm multiplying two things together. On the right side, I have a difference because I'm just subtracting two things from each other. So to get there, I will need to multiply these two things on the left side. Now, that's essentially just a foil or use the box, whatever. So let's go ahead and do this as a foil. So first times first. So I have sine of x y times sine of x cosine of y times itself, essentially. So that is a couple ways I can write that. I could either do sine squared of x cosine squared of y, which I'm going to do, or you could have written it as sine of x cosine of y squared. Okay, either one's the same thing. I'm going to leave it as it is because I noticed that on the right side, that's how it's written. So that's our first terms. Outside terms are these two. So sine of xy times cosine, sine of x times cosine of y. So this is going to be minus because we're going to multiply a positive times a negative. Sine of x cosine of y times cosine of x sine of y. That's ugly. All right, and then the inside terms, well, that's a positive times a positive, so that's good. I've got, so it'll be plus cosine of x sine of y times sine of x cosine of y. And then my last terms. So it's a negative times a positive, which is a negative. And it's really just cosine of x sine of y times itself. So let me write that down here below because I'm running out of room. So it'd be cosine squared x sine squared y. All right, and then once again, that would be equal to the box, okay? So, look, this looks terrible. But let's just really carefully look at what we have, okay? So I've got sine squared x cosine squared y. I don't see anything precisely like that anywhere else. So I'm just going to say, well, that can't be combined with anything. I'm just going to write it. In the middle, okay, sine of x cosine of y. Let's do this like this. Here's sine of x. Here's sine of x. Cosine of y. Here's cosine of y. Cosine of x, there's cosine of x. And sine of y, look, there's sine of y. What color have I not used? Green. Sine of y and sine of y. So I'm multiplying the same four things together. Remember, it does not matter what order I multiply them in. I'm going to get the same thing. And here, I'm subtracting that thing, and here I'm adding that thing. So this entire part of my expression just ends up being 0. All right, that's great. This is 0. So let's keep going. All I have left then is minus cosine squared x sine squared y. Now remember, I'm saying I have to get what's in the box. Now I have a little bit of space, so let me write what's in the box here. And some of you might be looking at what I'm writing and saying, well, Mrs. Kopp, that's exactly the same thing, isn't it? Sine squared x cosine squared y. Let me do that with a highlighter. Sine squared x cosine squared y. And then cosine squared x sine squared y. We got the same thing there, and we're subtracting them. So we were able to show that those two things are the same. Now, just a little aside, maybe you noticed up here, this expression is just a really complicated difference of squares, right? Sine x cosine y, sine x cosine y. Cosine x sine y, cosine x sine y. We're adding and we're subtracting. It's a really complicated difference of squares. And if you recognized that, then you could have skipped this step entirely, because you know that with any difference of squares, the middle terms are always going to be 0. All right, that's the end of introducing this idea of sum and difference identities. Next time we're going to add one more set of identities to our arsenal. Let us know if you have any questions.